talk, I'm going through the developments at the Canadian Geodetic Survey of NRCan on the use of 1 Hz GPS and GLONASS data of the real-time IGS network for monitoring ionospheric irregularities and TC mapping in near real time. So I'll go through some of the major steps that is being taken for near real-time monitoring using the real-time IGS network. Since considering 2 constellations now, I go through some bring your attention to the receiver and constellation-dependent background phase noise between different receiver categories in this network, as well as the 2 constellations that should be considered if we want to achieve the highest that we can get for ionospheric irregularity monitoring. And in the second step, of course, another product in near real time is the TC mapping from this network and the simple forecast model that I have implemented so that we can have real time and also future the rest of the day as well. And summary and conclusions is the last part, of course. So these are the major steps, not going through the details. Of course, usually 130 to 150 1 Hz stations are these days available at the RTIGS network. At every 15 minutes, we have 2 formats file, coefficients, spherical harmonic coefficients, spherical harmonic coefficients every 15 minutes, as well as Ionex, always containing 97 sets of maps, meaning that as far as we have real-time data, we have maps from the observations, and for the rest of the day, we have a simple forecast model so that at any time we have always 24 hours maps for the current day. In addition, as you can see, we are accumulating the sigma of delta phase rate, the sigma of geometry free, from 1 Hz data per 30 seconds, and we are accumulating our database over the past several years, and including GLONASS this year for all the 1 Hz data of this network for ionospheric irregularity monitoring in near real time, and for historical studies, we store them. So this is basically the sigma of delta phase rate that we use is the rate of geometry free. We kind of map it to the zenith using the same mapping function that we use for the TEC mapping. Here I use the Rtigs 2 terminology, even though I showed Rtigs 3 terminology as well. So these are L1, L2 on GPS and GLONASS. I'll shortly go through the impact that different receiver categories and also GPS versus constellation has on the effect, and things that we consider at Canadian Geodetic Survey for detrending these values before interpreting them as an ionospheric irregularity, so that we don't make a mistake, something which is not related to the ionosphere, but is a kind of receiver-dependent background phase noise or constellation-dependent, we will see shortly. But before talking about the combination of 2 constellations, this is the map on the upper left is the location of the real-time IGS stations during the famous March 17, 2015, also known as St. Patrick's Day's storm, the strongest storm of the current solar cycle. The colors shows the daily mean values of the SDPR. The table shows the receiver that contributed on that day, or at least those were available to me from the RTIGS network. The figure on the right, A on the top, is the daily mean values during the quiet day of previous day of the storm, March 16. Here, color-coded based on the location of the stations or the latitude of the stations, geomagnetic latitudes. And on the horizontal axis are the receiver categories as mentioned on the left columns of the table. So we had 7 categories of the receivers. You can see regardless of the ionospheric activity, comparing figure A and B, A very quiet day, B is the significant storm day. We have background phase noise for certain receivers significantly smaller than the others, regardless of the location and the amount of ionospheric activity. These are values that should be considered, and we consider for level the measurements so that when we look at the global scale, we will be able to compare everything in a leveled way. So now including GLONASS. So this is an example of the Canadian Auroral region. Usually we see ionospheric irregularities at this location because it's an auroral zone. 3 of the collocated stations at Yellowknife here is presented. You can see on the table on the top right, the receiver types and antenna types. We have 3 different receiver types here with different antennas, 2 same antennas, 1 other antenna. On the top left, you can see daily mean values of sigma delta phase rate over a period of time, as you can see from day 84 to 110 of this year. And the values color-coded are GPS average daily for different receiver and GLONASS average. On the bottom left, you can see we have a collocated magnetometers operated by Geological Survey of Canada of NRCan. You can see the max and mean of the magnetic perturbation mean subtracted. We have shown that in the Canadian Auroral zone, of course in Auroral zone, there is a close link between the ground magnetic perturbation and the GNSS phase irregularities, because magnetometers, of course, measure the ionospheric currents, and the ionospheric currents affecting the GNSS phase over the Auroral zone. As you can see, a very clear correlation between when we see higher values of the daily mean, let's say day 86, for instance, and when the max and mean on the bottom plot on the left is larger, means that has been a larger disturbances during that day, and a clear dependency that those daily mean values on the plot on the upper left are representative of the geomagnetic disturbances. There's a clear correlation between all type of receivers and all type of constellation, but we can see a clear bias between same constellation, different receiver, or different constellations, same receivers. As you can see, the yellow one, for instance, compared with the red one. The yellow one is YL3 GPS, the red one is YL2 YE2L GPS again, so the same constellation, the same press point distribution, but different receiver type. And this is the impact of receiver technology on the background phase noise that we use for detrending these indexes before interpreting them as an ionospheric irregularity. So let's just move, in addition to, instead of just one single station, here look at all RTIGS stations over a period of network time. This is plotted for day 110 of 2017. And on the right are the stations that contributed both GPS and GLONASS 1 Hz. Here there are 5 categories: Javad, Leica, Septentrio, TPS, and Trimble. And these are those that contributed in this specific day and color-coded based on the receiver type on the plot on the left. So here what is plotted on the right is the daily mean GPS on the horizontal axis and the daily mean GLONASS on the vertical axis over 61 days from day 50 to 110 of 2017. To be able to more conclusive, we have to look at figure on the left. Figure on the left, the horizontal axis is the daily mean geomagnetic latitudes of the ionospheric pierce point observed at each station. And on the vertical axis of the figures on the left are the ratio of the daily mean GPS to the same station daily mean GLONASS. So on the red horizontal line on each one is at 1, so it means that if the value is higher than 1, the daily mean GPS was larger than GLONASS, and vice versa. We can see that regardless of the location of the stations, which can be seen in the horizontal axis, and regardless of the day, certain receivers provided larger background phase noise for GPS, or almost the same, versus other receivers. For instance, Septentrio, clearly regardless of the location, regardless of the day of ionospheric activity, because this is 61 days, different activity levels, provided with a smaller value, meaning that the GPS background noise was significantly smaller than GLONASS, but wasn't the case for other receiver categories. And this is attributed to the receiver technology used in different receivers and their clock stability. Okay, considering these factors, we are using these for both constellation dependent and receiver dependent for detrending the ionospheric irregularity indexes. For detrending, this is an example of March 27, 2017, a day with moderate geomagnetic activity. On the top, only GPS values are used. Again, for all the RTIGS station above the geomagnetic latitude of 55 degrees, and on the bottom are the GLONASS ones, again, for the same day. What thing that you might consider from the figures on the right is the gap that we have currently in the real-time IGS network in that part of the northern hemisphere. But anyway, we were able to, after detrending, we were able to detect some irregularities. Hard here to see, even though I've plotted the larger values on the top pixels, but still the activity here wasn't that significant. In the next slide is more visible. When I summarize what we have seen on the previous slide, and that is using a certain bins of 1 UT hour by 5 degree geomagnetic latitude, and showing the percentage of value exceeding a certain criteria. On the very top is the Auroral electrojet index, some are familiar. For some who are not familiar, this is an index used in space weather, coming from a network of magnetometers over Auroral zone, and you can see can be clearly correlated with what we see in both GPS, the middle plot, and the GLONASS bottom plot, and they are agreed with the time of irregularities in this moderately disturbed day. Here I have another example at Yellowknife. Again, as we have a magnetometer at this station plotted on the top left, are the magnetometer irregularities, geomagnetic field variations at our magnetometer at Yellowknife. The middle on the left is the GPS only, the bottom left is the GLONASS only, and on the right are the actual pierce points. And we can see because of the geometry, there was a pierce points irregularities detected by the GLONASS because of the geometry at this period, which was able to detect an irregularity at the latitude band of 70 to 75 geomag latitude at the same period that we see geomagnetic irregularities at this period, and was able to see with the GLONASS pierce point geometry. So moving forward to the next part, how much time do I have? 3 minutes. Of course, in addition to the irregularities, we have a tech map in near real time, and recently I have implemented a simple grid forecast model so that if anyone is interested for the rest of the day, same maybe idea of ultra rapid, and we call this product EMUG, ultra rapid, because they are available in near real time and forecast for the rest of the day when the data is not yet available. And these are being forecasted from 15 minutes ahead to 24 hours ahead, and this is a quick validation. The top left is comparing this forecast from 15 minutes to 24 hours ahead with JPL. On the right is IGSG. The middle is final NRCan. The right is final code. And the bottom left is the near real time itself. And the figure on the bottom right is the KP index of this day, so that you can see it has been a day of quite an active day. That index, KP index, reached to exceeding 6 during the second half of the day. And the values plotted at the global mean on the red and the plus minus standard deviation on the gray error bars. Looking at the longer period of from March 21st to May 10, 2017, again, you can see that the day is degrading the mean, because they are forecasts shown here from 15 minutes up to 24 hours forecast. So every day you can see this discontinuity on the bottom plot, because they are degrading as far as we are far from the beginning epoch. And again, the STDs are plotted as a plus minus gray standard deviation. Another way of validating, the two top plots are basically the same. One is color coded based on 3 hourly KP index to see the activities every 3 hours. And on the right are the daily sum of the KP index, so that we have a single color per day. And the bottom plot is a summary of the top two. That is the maximum daily RMS, and conclusion is that up to 45 minutes ahead, this simple grid forecast was able to be within the 2 tech unit global RMS compared to with the actual observed tech maps, the tech maps that generated from the observations themselves. So, just to be on time, moving to the conclusions and summary. At the Canadian Geotic Survey of NRCan, of course, we use 1 Hertz in addition to our daily files, which use near 400 GPS GLONASS 30 seconds IGS stations, which I don't talk about that today. Regarding the real-time IGS, we use them GPS GLONASS for the near real-time TEC mapping, as well as the ionospheric irregularity monitoring for space weather applications. In this talk, I brought your attention to the impact of different receiver technology and different constellations that we consider for detrending our indices before using them for ionospheric interpretations. And when GPS and GLONASS phase measurements are used together, it is important that we consider these biases before going further. And when we consider those, GPS and GLONASS were able to overall were able to detect, similarly, we're able to detect irregularities, at least in the Canadian Auroral zone or high latitude, where we are mostly focused. The TEC mappings currently are being generated every 15 minutes, even though we have them in real time, and it's going to be available soon. And a grid forecast, a simple grid forecast model, also recently implemented for forecasting from 15 minutes ahead to 24 hours ahead. I would like to thank, of course, IGS and contributing organizations, and the AE data that you saw, Auroral electrode, are from the World Data Center for Geomagnetism, and thank you all for your attention.